Alright, welcome back to chapter 11 of the DB2 course. This is the continuation of our discussion of external merge sort. Okay, so I think we have a good general idea of external merge sort already. It's a rather I/O heavy algorithm, but it's really modest in space usage if it has to be. B equals 3 pages may be sufficient to perform an external merge sort on an arbitrary large table. That, of course, is the big plus for the external merge sort algorithm, but the number of passes will be high and the I/O performance will be abysmal, probably. All right, to optimize what we have so far, to look at more details at particular parts of the algorithms where we can tweak and tune things. To do that, I have recorded this particular video, and I would like to address two bits of the external merge sort algorithm that we can tweak and tune and improve. The first bit is related to the I/O access patterns that we will see when we perform external merge sort. The I/O access pattern in pass 0 and in the other passes, pass 1, pass 2, and so on, they will be different. So in pass 0, what we will see is that the input file, the heap file T, will be divided into partitions, into capital R, many partitions. Each of these partitions has a size of capital B pages. Right, we will read such a chunk or such a partition of the input file in one go into the working memory, have it sorted there, and then written into the output. This is a rather favorable input-output pattern. We will read a chunk, an adjacent chunk of B pages from the input file. Well, B may be larger than 3, maybe B is 100 or maybe B is 500. So we would read an entire chunk of 500 pages, adjacent pages from the input file, and have them loaded in one go into the working memory. This is blocked I/O, this is batched I/O, and this is a really favorable I/O pattern. So all in all, I would give this a thumbs up. Right, so there is not too many seeks to be performed. It's exactly R seeks, capital R seeks, the number of runs many seeks have to be performed. Each of these seeks will lead to a batch of I/O operations or batch of block reads. Let's call it this way, and this is thumbs up. In the other passes, in the passes 1, 2, 3, and so on, when we have to perform the merging, things look different. We will perform B-1 way merges. So B-1 runs or sorted mini files on the external storage will contribute to the merging process. Which of the B-1 runs can contribute its next page that will be then loaded into the working memory is completely unclear. The operation of the priority queue that will pick one particular value, which is then moved into the output, and spot will open in the priority queue, and one of the B-1 runs will contribute its next portion of input to the priority queue. All of this is very hard to forecast. It's impossible to forecast, actually. Which of the B-1 runs will contribute is completely open. And if I know that one particular run will contribute, it will contribute the next page, the next block of rows only. So there will be no batched I/O, and there will be random seeks seeking to run 1, seeking to run 42, seeking to run 1 again, then to run 23. It's all unforeseeable, and all of these seeks will only lead to a single page I/O. I would say this is a thumbs down I/O pattern. It's really the worst I/O pattern that we can imagine on an external device that has to perform seeking. Okay, so one idea that we can pursue here would be to use blocked I/O during the merge passes. Blocked I/O refers to the idea of not loading only a single page from these runs, but at each time read B greater than 1. So I'm talking about the lowercase b here. B greater than 1 pages at one time if we access each run. Okay, so if a particular run contributes in one of these passes here, then it will not only contribute a single page, it will contribute B pages. These B pages are loaded in one go. We will seek to the correct position in one of these runs, the next run that has to contribute, and we will then read B pages from that run. Okay, so the seek cost is really way better amortized. It's not one seek per IO, it's one seek per B IOs. So in effect, the page IO cost, or the per page IO cost, is reduced by a factor of lowercase b here. Okay, so that should alleviate some of the overhead that we have seen with our single block reads from the individual runs. Of course, well, we will have a reduced fan-in during the merge paths. Okay, so because each of the contributing runs will now contribute up to b lowercase b pages into the buffer, well, we have to accommodate and have to allocate b lowercase b pages in the buffer for each of the contributing runs. This means that the fan-in, the number of runs that can contribute at any time to our merging process, is exactly this number. It has been b minus 1 before, it's now b minus 1 divided by lowercase b. So each of the incoming runs has an allocation of b pages in our buffer, and well, this will reduce the fan-in. Okay, and the reduced fan-in means we can merge fewer runs in one pass, and this will indeed increase the number of passes that we will need. So there is some interplay between the number capital B, the large B that defines the size of the buffer. There is an interplay, of course, regarding the number of pages n that we have to sort overall. There is an interplay with the lowercase b, now our blocking factor that determines how many pages are to be read in one go from each run. So this leads to a rather complex interdependency of all of these parameters and the tuning knobs that we have to configure our external merge sort behavior. Because of this, what I've brought with me here is this interactive web page that you could use to play with all of these parameters, to adjust them, to adapt them, and then to see what consequences all of this has on the number of I/O operations, on the number of disk seeks that will be performed, on the number of passes that will be needed, on the number of, or the size of the fan-in, the number of runs that can be merged in each pass, and so on. So let's try that. Let's switch over to this interactive web page here, and well, you can see that the parameters that define our external merge sort, they have been reproduced here. For example, the size of the buffer B here is currently configured to be 128 megabytes. Well, it has only been 4 megabytes in the default configuration of PostgreSQL, so we could try to adjust this. So we could just use this slider to adjust the number of pages in our buffer. Well, we could also adapt the size of our database pages. We know that this is 8 kilobytes in the PostgreSQL default configuration, so we could leave it like this, but we could drag here and change the database page size. We could configure disk characteristics like the seek time, which will be super relevant in this setup, the average read-write speed per megabytes. This is something that we can configure. We could, of course, also configure n, the number of pages in our input file. So given that the input file is 8 gigabytes, given a database page size of 8 kilobytes, this leads to 2 to the power 20, or about 1 million pages in the input file. Right, so all of this defines the input and the behavior of our algorithm. The observed output and the I/O performance of that algorithm is then to be seen below that line here, the resulting external sort behavior. So you see that in the current that in this current configuration we would need one merge path, and that merge path would have a fan-in of 16,199, which is of course is a consequence of the capital B being 16,200. This would be a B-1 merge. Okay, why is this a B-1 merge? Because the blocking factor is still just a single page. Now we could play with all of these parameters and then see how the number of merge paths, the fan-in, the number of I/O operations, the number of disk head seeks, which is really large here, is changing. And here's also some rough time estimate of how long we have to wait until all of the input would be sorted. So let's first reduce the size of the buffer here to something that would be more reasonable and closer to the PostgreSQL default. So let's go down to maybe, okay, drag some more here to 4 megabytes maybe. Can I do that? Yes, I think so. About 4 megabytes here. All right, so that would be close enough. That's close enough to 4 megabytes. All right, so you see that we already need 2 merge paths now, and the fan-in is 499. Of course, it's B-1. All right. Well, the number of disk head seeks is phenomenal. It's it's more than 4 million disk head seeks, and this is the number of I/O operations, which is of course defined by the number of passes that we have to perform here. All right, so now let's play with the blocking factor, and let's not read a single page from each of the runs when they contribute to the priority queue, but let's read 16 pages maybe. And you can observe how the fan-in is reduced, 16 pages, and the number of merge paths increases, but of course the number of disk head seeks, 16, the number of disk head seeks went down to to less than 400,000, and indeed the overall time to process to sort the entire input file has gone down too. So I can only invite you to play with these parameters, have a larger blocking factor maybe of 32, okay. So this means that fan-in goes down once more, less disk head seeks, and well, yeah, maybe better overall times here. Well, we can increase the blocking factor further, but then this will lead to a higher number of merge paths, which will increase the number of I/O operations and so on. So the interplay is really interesting here. I can only encourage you to play with the parameters. Okay. So that would be the impact of the blocking factor when we read the input runs during merging. There's one other detail I would like to look at here, and this is the pass 0. So while the blocking factor has been an optimization that impacted the passes 1, 2, and so on, also pass 0 can benefit from some tweaking and tuning here. Okay, of course, the initial number of runs that we create in pass 0 influences the overall sort performance and the duration of the overall sort algorithm. This is the number of I/O operations that we will perform. All right. In each path, this is the number of paths. In each path, we will read and write the entire input file, or runs that comprise parts of that input file. So we read and write the entire input file, so each path will lead to 2 times n I/O operations. This is the number of passes. All right. What I'm talking about here is this highlighted piece of the formula. This is the number of runs created in pass 0. Okay, so how did we arrive at this particular number? Well, it's the size of the overall input file divided by the size, capital B, of the input buffer of the working memory. So chunks of size B would be loaded into working memory to then be sorted by some regular in-memory sorting algorithm, maybe quicksort. And since this is all the space that we have available inside our working memory, You may think that, well, of course, partitions cannot be larger. Partitions cannot be larger than B pages, so this will be the entire number of partitions that we have to create. But, well, one could ask yourself, is this really the best we can do? Given B buffers, is the creation of initial runs that are of length B pages, is this the best we can do? And the answer is no, you can do better. There is something better that you can do. Instead of quicksort in this pass 0, use a different sorting algorithm. For example, the so-called replacement sort algorithm, which can lead to passes, which could lead to runs, which could lead to runs in pass 0 that are longer than B pages, significantly longer than B pages. All right, let's try to sketch replacement sort here. Okay, so recall that we are in pass 0 now. So what we are trying to do is to read from our unsorted input file, and create chunks of sorted runs, sorted portions of the file that we then call runs. Okay, so what we will do here is we will organize our buffer in terms of a priority queue again. So B-1 buffer pages will again be used and operated in terms of a priority queue. But since we are in pass 0, there will not be multiple runs contributing to this priority queue, but only the unsorted input, the single heap file, the heap file for table T. This will be the single input that is relevant in this particular pass of the algorithm. Okay, so we will operate a priority queue as we have already seen it in the previous video. All right, there will be one additional annotation on the elements that are placed in this priority queue, and this is mentioned in the bullet point 1 here. Well, we will have this small plus sign annotated at the elements in our priority queue if they arrive too late to be now placed into the output sorted run. Okay, so that will be the output of the sorted run. Of course, there will be the largest element that has already been placed in the sorted output run. Any element that will find its way into the priority queue that is less than this largest element already placed in the sorted run will be arriving too late in a sense. It will be marked with a plus sign and handled specially. It will receive lower priority. It will not be sorted to the root of the priority queue where we pick the next element to push into the output sorted run. Okay. At one point, you will see that all of the elements in the priority queue are marked with a plus. All of them have arrived too late to be included in the current sorted run. At this particular time, we would close the current sorted run, call it a day for this run, and just open another run. Okay, so to make this more concrete, let's look at a tracing example. All right, so this would be the initial setup. This is the input file T, which of course is entirely unsorted before we enter pass 0. We will again maintain an input pointer, a read pointer, which is of course at the very beginning of the file. Our B-1 pages in the input queue are still empty. This is the last page of our buffer, which of course already still is empty because nothing has been placed there yet. All right. Right, so we would start and load the queue. So you can see that at this particular point, the queue is already fully loaded. We have consumed 3 elements from our input run. And indeed, our read pointer has moved by 3 positions here. There it is. Okay. Right, so we will now operate our queue normally, and the element at the root will be placed in the output. All right. We will then reorganize our queue. There is some empty spot here at the root. It will be occupied by the 3. And now there's some empty spot here that can be filled with the next input element. Okay, the next input element, looking at our input file, is 4. And indeed, it will be placed in the empty spot here. Right, now it's time again to take the root element, place it into the output run, 2, 3 here. An empty spot is time to place the next element from our input file there. The next element from our input file is this 1 here. Okay, so it will be placed in the empty spot. Okay, so this one arrives too late. The largest element that we have written to the output queue already is already larger than the one that we have just read here. This one has arrived too late for inclusion in this particular sorted output run. Okay, so it will be marked with a plus. This marking will lead to leave the one in its original spot here, and it will not be sorted to the top of the priority queue. All right. So instead, the 4 will be moved into the output run. Okay. So an empty spot is now opened. The empty spot will be filled by the next input element, which is the 2. The 2 is placed here. 2 is smaller than the current element that we have, the last element that we have outputted here to the sorted run. So the 2 arrived too late. Indeed, it's annotated with a plus here. It will not be sorted to the top of our queue. Instead, the 6 will be output into the sorted run. There it is. And the empty spot of the 6 will be filled with the next input element, which is the 7. The 7 has been placed here. 7 is larger than the largest element in the sorted output run. The 7 arrived just in time, and it can be written into the output run. Okay, its empty spot will be taken by the next input element. 3 is the next input element. 3 arrives too late because 3 is smaller than the largest element in the sorted output, which is 7. All of the entries in our queue are now marked as plus. All of them have arrived too late. At this particular point, it's time to close the current sorted output run. The sorted output run number 1 is finished now. We will close the file, okay, and have now created this particular sorted run. And the next output will be written into the second output run, which we've already opened here. Of course, all the plus signs can now be removed. Everything is now reorganized according to its key or sort key value, and of the next value to be written into the second output run will be the one at the root here. Okay, so as you can already see, well, our B has been 4 in this particular example. The output run that we have created is indeed already larger than B. So the real effect of replacement sort can only be seen if you consider larger B's here, and I can only invite you and try to implement or play with this. I think there will be an assignment that asks you to re-implement a simple version of replacement sort on your own. And then you will see that the length of the output runs that we can create is about 2 times B minus 1, which is of course larger than B. So indeed, we are able to create sorted output runs given only space of B slots in our working memory. And this is of course good news. It will lead to a lower number of runs that are emitted by pass 0, and thus to an overall lower number of runs that have to be merged in the passes 1, 2, and so on. So that can be really a substantial win when it comes to the performance of external merge sort. Okay, there's some considerations here regarding replacement sort. Replacement sort behaves particularly well, as you can imagine, if the input that flows into our priority queue is already partially sorted. Then the sorted output runs can be considerably longer. Well, such situations are not too uncommon. So maybe we are about to recluster a particular file that once has been organized and sorted according to a given sorting criterion. Some of the rows or some updates have been performed, some of the rows have been changed, maybe some rows have been added to the end of the file, but the lion's share of the file will still be sorted. If we sort such files or cluster these files using replacement sort, then we will see quite favorable, quite interesting, very good behavior there. The creation of very long initial runs in parse null. All right. So that's about external merge sort and some tweaks that we can do to this particular algorithm. In the upcoming video, we will look at grouping, which is an operation that of course can benefit from the existence of replacement sort. We will also consider hashing when it comes to grouping, and we will also consider the parallel evaluation of grouping. But these are topics that are reserved for the upcoming videos. So stay tuned if you would like to hear about this. See you there. Bye-bye.